The following video highlights the main concepts to know in section 2.4 for pre-calculus, average rate of change. I'm going to start with just a simple, I'll call it a word problem, and this will be used to demonstrate some of the concepts of this section. Let's assume we're traveling from Maryland to Massachusetts on a car trip that's going to take about 480 miles in total. After 4 hours of driving on the first leg of your trip, you've reached the outskirts of New York City, having covered 220 miles. After 4 more hours of driving on the second leg of your trip, you reach your final destination in Massachusetts. So with that as background, here's a couple questions. What was your average speed during the first leg of your trip in reaching New York City? 2, what was your average speed for the entire trip? And finally, 3, what was your average speed for the second leg of your trip, depart from New York City to Massachusetts? So let's look at this in a little more detail, and I've put the calculations down. We've probably been able to do most of these in our head, but by working through this example, it'll map us nicely into the concepts of section 2.4. For the first question, the average speed on leg 1, we simply need to figure out how many miles we traveled and divide by the number of hours that we spend traveling during that portion. We know that it took us 220 miles to reach New York City, and it was 4 hours of driving. So our average speed was 220 miles divided by 4 hours, and that gives us 55 miles per hour. That was our average speed for leg 1. It's a similar calculation for question number 2, the average speed for the entire trip. Well, we started at mile 0 and we finished at mile 480, so we know we traveled 480 miles, and we know that the full duration of our trip was 8 hours. So our average speed for the full trip was 480 miles divided by 8 hours, and that gives us an average speed of 60 miles per hour for the full trip. Now part 3 asks us for the average speed of just leg 2. So what we need to do there is use the information we have to figure out, well, how long was leg 2? We know our whole trip was 480 miles, and we know it was 220 miles to New York City. So as a result, leg 2, its length in miles was 480 minus 220, and that's 260 miles. Again, from the problem, we were told leg 2 took 4 hours, so our average speed for leg 2 was 260 divided by 4, or 65 miles per hour. Now we could have put this into a table, and that's what I'll show on the next part, and done our questions in a slightly different fashion, but we would wind up obviously with the same answers. We could create a very simple table showing a functional relationship between x, our number of hours, and our y value, the miles traveled. You'll also note we just kind of refreshed the numbers as we had on the previous piece of paper on the screen, and obviously we had all the same answers. One thing to note, our numerator in each of these calculations, or in each of the calculations for these questions, represents what we saw in section 2.1 that was called the net change, where you determined where you were at one point in time against another point in time and determined what that change was, hence the term net change. So this kind of serves as an introduction to section 2.4, and the concept that we've really seen here is for the average rate of change of a function is something that we actually just were representing. It kind of represents, for lack of a better term, how far you've traveled along the function versus the amount of time that you've gone along the function. And that's what we're seeing here when we're trying to calculate the average rate of change for a function, f of x. It's simply your change in y value over the 2 points in question, which are called points A and B. And that's versus the change in your x-axis, in other words, b minus a. When you go from A to B, the distance you travel is b minus a along the x-axis. In looking at it from a functional standpoint, the difference in your y values is f of b minus f of a. And so that essentially is where that average rate of change calculation comes into play. Again, the change in y over the change in x as highlighted up at the top of the paper, and then that translates into f of b minus f of a over b minus a. So let's use a couple problems just out of the book to illustrate this concept a little bit more. The first one talks about changing water levels. The graph shows the depth of water in a reservoir over a 1-year period as a function of the number of days since the beginning of the year. Obviously, the water level fluctuates up and down as the year goes on. What we're asked for here, what was the average rate of change of the water level between x equals day 100 and x equal day 200? So I've highlighted the 2 points on the graph and colored them in a little bit more deeply so they can be seen a little bit easier. The 2 points on the graph are x equals 100, w equals 75. That's our first point. And then the second point is x equals 200, w equals 50. So we're really trying to analyze what took place in the water level between those 2 points. Using the nomenclature that we had, you know, A and B, f of A, f of B, we can go ahead and plug in values here for our points. We'd be saying that A equals 100, that's our starting point, that was day 1. And f of A, which is a starting value or what we saw for the water level at that point in time, was 75. Similarly, for B, we know that B is equal to 200 because it was day 200 that we're being asked about. And we know on day 200, the water level, f of B, was 50 feet. So to look at that average rate of change, it simply becomes just plug in those 4 numbers that we have. So we wind up with f of B minus f of A, giving us 50 minus 75, divided by B minus A, namely 200 minus 100. When we calculate through on that, we get negative 25 over 100, or negative 1/4. So the average rate of change that we would be seeing here between those 2 points, between day 100 and day 200, is negative 1/4 foot per day for the water level. So again, there was that problem. I took one other one out of the book, and this is from page 214, number 18. For this problem, we're being asked to analyze both, 1, the net change, as well as B, the average rate of change for this function across 2 values of t equals negative 2 to t equals 2. So for this problem, A equals negative 2, B equals 2, and then I'll go ahead and calculate f of A as the problem laid out. F of A is negative 2 to the 4th minus negative 2 cubed plus negative 2 squared, which when all is said and done gives us 16 minus negative 8 plus 4, or 28. For f of B, or f of 2, we have 2 to the 4th minus 2 cubed plus 2 squared, which will give us 12. So now to compute the net change, it's simply f of B minus f of A. In this case, that's 12 minus 28, or negative 16. For our average rate of change, it's simply that same number, that negative 16, divided by B minus A, which in this case is 2 minus 2, which gives us 4. So our final average rate of change becomes negative 16 over 4, or negative 4. So that, in a nutshell, is the concept of average rate of change. On the notes packet, we can go back and I will go ahead and complete some filled-in notes, and we will focus on examples 1A and 1B, as well as 2A and 2B. Those will be the key things to focus on here in terms of understanding average rate of change of a function.